as if browser bugs weren't bad enough, I'm here to present an attack which exploits a browser without requiring any bugs in the browser. So I'm going to abuse a deduplication side channel, which together with Rowhammer, which is a hardware bug, and together they allow us to exploit a modern browser, Microsoft Edge, without the use of any additional bugs in the browser itself from JavaScript. So in short, how are we going to do this? We will use the deduplication side channel attack to leak information, so leak a heap pointer to data that we control, and then combine this with a code pointer, a pointer to the browser's JavaScript library, and these two secrets allow us to create a fake object, and this fake object we will use Rowhammer to flip up a bit in a pointer to make to get a reference to this fake object, and this fake object will allow us to have an arbitrary read-write primitive and own the browser. So how does this deduplication side channel attack work? Well, say an attacker has control over some memory, and a victim has its own memory, and the attacker wants to know whether a certain picture is inside the address space of the victim. So in this case, it is. What the attacker does is recreate the pages that it wants to probe for in its own address space, and then it waits for the operating system or a hypervisor. So, for example, Windows 8.1 and higher have this feature, as well as some virtualization some hypervisors. They will scan memory and identify pages which are similar, and will point all the memory to the same place, and this saves memory. But the problem is, so the kernel or the hypervisor will mark this memory copy on write. So why is this a problem? Well, if you do a normal write to a memory page which is not marked copy on write, it will go very fast, and then but the deduplicated page has to be copied first before the write can happen, and this takes longer, and this takes longer, and you can measure this from JavaScript. So this is all nice if you want to leak the content of an entire page, but can we generalize this to leaking a small bit of information, like the randomization in a pointer or a password? So turns out we can, but there are some challenges that we have to overcome. So first of all, a small secret does not span an entire page. So we need to turn this secret into a page. So we need to find a way to get a secret together in a page with all known data, so that we can protect, we can predict what the whole page looks like. Another problem that we can have is that the secret has just too much entropy, and if we want to scan for every possible value of this secret, we exhaust our memory. So to solve this, we have in the paper we have three primitives which will help us with finding out the secret nonetheless. One is we control alignment of the secret, where we only have part of the secret in a page, such that we can leak the information in 2 or more steps. And this allows us to this allows us to reduce the entropy and leak the information. We have a second primitive, which where if you cannot control the alignment, but possibly overwrite part of the secret in memory, we can reduce the entropy that way. So for our browser attack, we use the first method of controlling the alignment. We make use of the JIT function, the compiled JIT function epilogue in Microsoft Edge. And because we control the function, we can create functions which are just slightly larger than one page, so that the function epilogue is on the border of a page. And then some of the functions will have the code address which is in the function epilogue. Actually, we know all information in the epilogue except for the code address. So that's what we want to leak. So if we create a JIT function with the code address just on the boundary, we can leak this code address in multiple steps. So, and then every step we can fill in the parts that we already know. So then there's a final possibility that we cannot override part of the secret or align this, something. Are we then lost? This is not always the case. So in the case of finding our heap pointer in our browser exploit, we couldn't find an alignment or a way to control the alignment or to override a part of it. But then there's another solution. So we can still leak a heap pointer by making use of an observation called the birthday problem, which tells you that a surprisingly small, given a surprisingly small group of people, the chances of two of them having the same birthday gets really high relatively soon. And the underlying intuition about this is that you're not doing one comparison of someone's birthday with someone else's birthday, but you're doing all comparisons at the same time. And if you think of it, memory deduplication does this as well. So we abuse this functionality. In this case, we're leaking pointers, so we generate lots of pointers. Any of them will be the pointers to objects that we control. Any of them will be OK for us. At the same time, we probe for lots of pointers, and we only have to have one match. And this match will be done by the deduplication mechanism, which does this any-to-any comparison. So in memory, it looks like this. We have pointers to real objects, and then we guess pointers to fake objects, and then we just create some of them. And after not that many, we don't have to create that many to get a hit. So the duplication mechanism makes sure that both pages point to the same physical page, and then we can do our deduplication test by writing to it and get the memory. So now we have leaked the code pointer and the heap pointer, so we can create a fake object, which allows us to do read-write. But we still need a reference to it, and the JavaScript engine, for good reasons, doesn't allow us to do this. So what we do is we create this object inside an existing data structure, a JavaScript array, and then we have another one right next to it. And now we need to pivot a reference to the second array onto the first, onto our fake object. And we do this by inducing a bit flip using Rowhammer. So Rowhammer is a hardware vulnerability where the observation is that if you access a certain row in memory very quickly, in quick succession, the neighboring rows experience interference, and some of the neighboring rows bits can flip. So in our case, we use this bit flip to so we find bit flip memory that you can flip, and then we insert the right pointer in this memory location. We hammer, the pointer flips, and we get a pointer to our object, and then we can have arbitrary read-write. So in short, memory deduplication is a way more powerful side channel than previously thought. In our paper, we also have an example of leaking information from a different process. It's possible to do reliable browser exploitation in JavaScript. That's it. Any questions?
Hey, thanks. So how long do each of these two parts of the attack take? So how often is the OS or the hypervisor doing this deduplication? Because you have to guess a lot of values.
In Windows,
and then, okay.
In Windows, it's every 15 minutes as we tested.
Every 15 minutes?
Yes.
But don't you have to like guess 2 to the
at
least 8, if not 16?
So we haven't studied the exact mechanism with which it is being done in Windows. In Linux, it's being done every once in a while. They merge several small pages. They just scan the memory and merge pages.
Right. And then Rowhammer flips a random bit, and then you have to check, was I lucky? No, try again. So how long does this whole attack take?
It depends on, so the deduplication attack, it takes about 30 minutes. We need 2 sweeps for the code pointer. So, and then the Rowhammer attack really depends on how vulnerable your memory is to Rowhammer.
Right. Okay.
Hi, my question is more related to the Rowhammer. How did you reliably find that if one bit, I flip this bit, it's going to convert into a pointer to the other location? Because you need reconnaissance first, right? You have to recon.
So there, the description is in the paper, but what the just is that we, in Edge, you can have pointers and double values in the same location, in the same type. So we put a double value there, and that we can completely read. So we do Rowhammer, and then see if the double value changed, and then see which bit changed. That's kind of interesting. If you do Rowhammer, it's usually the same bit that flips again and again and again.
And it's direction also.
Yeah.
So if one bit is changing
so we have doubles in an array, and then when we know which bit flips, we put a pointer there, a reference to an object, and then so in Edge for this you can put that in the same location, but the details are in the paper.
So my complementary question to that is, the same physical page was being used when you're doing the attack?
Could you repeat that?
So first time you do the recon that, okay, this bit is flipping, and once you know the knowledge that this bit is flipping, after that you have to reuse that physical page. You have to force the system to reuse the physical page for the same data object. So what behavior you saw there? Was Edge using the same physical page?
Oh, so the Rowhammer, so actually for Rowhammer, we make sure that Windows doesn't dedupe the pages we're Rowhammering, otherwise it will screw up otherwise it will screw up the whole, the measurements will, the Rowhammer will not work anymore, but so it's always the same page so if you find a bit flip using, so you hammer one location, or it's actually two, but and then it's and then the neighboring rows will get bit flips.